Check.
Great. Hello everyone, and good morning, afternoon, or evening, wherever you are. I'm going to talk about Fermi bubbles, mostly the observational sites, and I have been suggested that this should be a tutorial rather than a talk. So this is really an introduction to the people, to the Fermi bubble, for the people who want to think about it, but have been so busy that could not dig into the topic much. So this is perfect. This will be perfect for them to start thinking about this topic. Also, I have to be very careful about speaking few things, because some of the observations that I am going to mention are things those were worked out by some of the people who were already in the audience. So if I say anything wrong, they may actually throw punches at me even through the screen. So okay, let's begin then. So this whole thing started. This whole thing started with the discovery of two giant gamma ray bubbles in the galactic center, towards the galactic center. So this was first discovered in 2010 in the 1.5 year, roughly 1.6 years of data from Fermi Lab telescope. And what they found was something which is very exciting, and which revived the whole topic of discussion of activity at the galactic center. This is a more recent data map by Ackerman et al., which has, I think, 4 years of data. So this shows on the right hand side, this shows these two very eye-catching bubbles at the coming out of the galactic center, and they're very perfectly symmetric, almost equal shape, and then size. Their surface brightness hardly varies across the surface. Okay, so these are called the Fermi bubbles. Okay, apparently, if you calculate the distance, size, and convert it to distance, the sizes are roughly 8 to 10 kiloparsec. In the lower energy side, there's something called loop 1, which is also seen in this map. It shows this nice two horn-like structures, but upper edge is not very clearly seen, but you can see there is some kind of shock. The southern structure is not seen, if there is any shock or not, but there are two horn-like structures which are exactly symmetric and of the equal shape, like the northern horns, but in the southern hemisphere. So the total gamma ray intensity, total gamma ray luminosity from this Fermi bubbles is actually about 4 times 10^37 arcs per second. Okay, the total mechanical luminosity, if you only consider the bubble region, which is converted from how much X-ray emitting gas you see, etc., and the size, it turns out to be about 10^54 to 55 arcs. Sorry, this should be a total energy, not per second. 10^54 to 55 arc amount of energy. If you also consider the loop 1 feature, or the north polar spore, which is again a debated topic, the total energy comes out to be about 10^55 to 56 arc. Okay. So what I'm going to do, for the tutorial sake, is I'm going to take all this observational evidences and put them into cartoon, because I don't have so much expertise into creating this combined or multi-wavelength maps. So I'm just putting them in the cartoon. So this hash region you see is the hard gamma ray, which is more than 5 GeV, anything emitting more than 5 GeV. And this golden ring that you see on top is the loop 1, which is soft gamma ray. Okay. So the observations also had, like, before gamma ray observations, we also had some information about the different structures at the galactic center, which are basically X-ray or radio emissions. But the topic was not that highly discussed because it was not sure whether the X-ray is coming from the galactic center or not. So it was discussed, but the whole thing got revived after the discovery of the gamma ray bubbles, really. So what we see here on this left, most top left plot is this X-ray emission from E Rosita, okay, in 0.6 to 1 keV band, which is soft, and you can see this nice North Polar spore, which also comes around. But the new thing in the Rosetta we find is this this southern shock or shell-like feature, which was not visible in Rosette. Okay, so which is encouraging. In the lower energies, like if you look at the microwave, like 23 to 60 gigahertz maps, this one is particularly from Planck observation, and what you find is that this nice excess emission, which pops out of the in excess to the CMB emission around this frequency range, which is almost co-spatial. Okay, so this is highly likely that the both the microwave and the gamma ray are actually coming from the same underlying electron population, which is very likely. And the spectral index for this electron population is about -2.2. Okay, we also see in polarized emission, radio emission at 2.3 gigahertz that this radio emission is actually extending further out from the Fermi bubble towards the top. Okay, so what I'm going to do, I'm actually going to put all these things into again in the cartoon. So the blue is now X-ray, which you see this nice two Rosetta-like bubbles, and then in underlying we also have microwave emission, which is the radio emission in general, which is represented by the green patch. Okay, so let's move forward. So one thing that I mentioned is that the X-ray, the weather, what are the structures which are seen towards the galactic center in X-ray, whether they're related to Fermi bubble or not, has been a big discussion. It actually has been argued over half a century now that no one has really a good answer or a clear consensus. What is it? Today we find some results, observations, which say that this X-ray are actually coming from galactic center. Someone says that some other observations come in on the next day says that no, these are actually close by. So this is really being debated for over half a century now. So there are actually two kinds of scenarios where you can have these X-ray shells towards the galactic center. One is that it is actually originated at the galactic center. So the size is about 8 to 10 kiloparsec. At another is it is actually close by, which is close to like 100 to 100 parsec. But the size is also comparable, 100 to 100 parsec. It's simply that it is projected on the same physical space, sky space as Fermi bubbles, which is giving rise to this confusion. So I actually wanted to dig into this topic at why, what is the origin or something. And it turns out that, I listed some of them here towards in favor of galactic center origin and local origin, and you can find your favorite observation, but it seems that this is not yet settled, and I don't know which is true, but somehow I prefer the galactic center origin picture, but this is again something which has to be done through observations, and it is better to leave it to the observers who can actually resolve this issue. So one thing I want to say that the main, it seems that this debate is going on because the two kinds of observations are saying two different things. Like the main proponent of galactic center origin is coming from X-ray emission, X-ray absorption towards the North Polar spore, whereas the radio absorption, radio emission, or the radio Faraday depth, depolarization, etc., which are actually coming saying that these structures are closed by. So I think it is still best to leave to the observers to find out what is the true distance to it. But let's move on to other observations. So Fox et al., Andrew Fox and Rongan Bordola, they had this nice set of observations which look at the background AGNs to find certain absorption lines, absorption line profiles through the Fermi bubbles, and this is what they find. And they find that there are actually sufficient number of clouds which have absorption lines more than the what you would expect from the background clouds. So this says that there is an excess of clouds within the Fermi bubble, and the kinematics of this clouds show that the line of sight velocities can range from -200 to +250 kilometers per second. And if you model the kinematics of the clouds, assuming momentum driven or energy driven, turns out that the radial velocity for the cloud, if you assume that these clouds are completely radially outflowing, this is about 1,000 kilometers per second. And it is a simple task from there that to divide the distance by the velocity to estimate the age which the clouds take to reach 10 kiloparsec from the galactic center, which is about 6 million years here. So let me put this clouds on top of this cartoon over here, which will turn out to be a complex picture later. So these yellow clouds, you can see they are actually within the bubble, and I have not plotted any bubbles on any clouds on top of it, because the detection rate is lower compared to within this bubble. So looking at the H1 emission, this is a result from Lockman and McGriffiths, who find that the galactic center has a huge hole in the H1 emission. And this is what is shown over here. And the outer edge of the Fermi bubble is shown by this red dotted dots. And there is another X-ray structure which is called the northern arc, which is shown by the cyan lines. But surprisingly, this is actually of the size of about 2 kiloparsec in radius, okay, which is huge. So, okay, so we also have individual H1 emitting clouds towards the galactic center. This is an observation from the Theodoro, who find that these small clouds, which have actually roughly an opening angle, you can see that this roughly corresponds to a certain opening angle, which is, it seems that the clouds are actually being accelerated from the galactic center and flowing out. Okay, and the velocity of these clouds also seem to be varying from -300 to +300 kilometers per second. Okay, so the luminosity, mechanical luminosity for these clouds is simply the kinetic energy, is about 3 times 10 to the 40 arcs per second. It has to be more than that. And this, the kinetic size that these clouds have been traveling for about past 10 million years roughly. So I'm going to put this, H1 hole in the galactic center and the small scale clouds, which are also, found in H1 emission. So let's then move to know what is happening at the galactic center. So if you look at, zoom into the galactic center in X-ray, so this is an image from ROSET in 1.5 keV, and it shows that this nice conical X-ray shaped outflow happening from the galactic center. If you put at the, overplot it with the gamma ray emission, it seems that this nicely matches the gamma ray emission. It seems that the X-ray and the gamma ray at the galactic center also has a common origin. Okay. Moreover, if you look at even deeper, using XMM Newton and radio emissions, you can find even more, and interesting structures. For example, this left figure is from Ponte et al. 2019, and what they find is that in radio, which is the green, which is the green color here, in radio you clearly see a shell-like formation, okay, at the galactic center. So this Sagittarius A is roughly here, and in X-ray you find chimney-like features. So this pinkish reddish color is the X-ray sulfur 15, I think sulfur 15 line emission obtained from XMM Newton, and you can see that it seems that something is coming out of the galactic center. Okay, and in this small scale, you also have active galactic activity. Preferably from the Sagittarius A star, but there are other explanations too for this chimneys, whether they can be produced by supernova activity at the galactic center or not. So all good. Now, what are the other effects that we have that says that what is happening at the galactic center? Recently, there was a paper by Blandhofen in 2019, which last year, who find an excess ionization. I think this figure should be upside down and like reversed. So this is the LMC, and they find that the LMC, certain part of the LMC has actually excess ionization, and this cannot be produced by simply star forming clouds. I mean, star formation at the galactic center, you need something which emits hard ionization photons. So this is only possible from AGN if the galactic center AGN was active. And by calculating the travel time from the galactic center to the large Element Cloud and to us, and the recombination time given the suddenly ionized gas, they estimated that this must have happened about 3 million years ago at the galactic center. So the galactic center black hole must have been active 3 million years ago with a luminosity of 0.1 to 1 Eddington luminosity. So there must be, so it is clear that something is going on or actually went on at the galactic center about a few million years ago. Okay, so I'm just going to put this LMC, in this patch just to show that there is an excess ionization that is required to explain the ion ratios. Right. So what else do we know from the galactic center observations? Like if we can look at the fluorescent iron lines, and it turns out that it suggests that this iron line suggests that the luminosity of the central AGN was about 10 to the 3 to 10 to the 4 times higher compared to what we see currently, which is about 10 to the 38 arcs per second. So this means that the past luminosity could have been about 10 to 41 to 42 arcs per second. Okay. There is also a smaller clump of stars, newly formed stars, which formed about 6 million years ago, which is within the 1 parsec region of the galactic center. So this means that something definitely went off there and something happened with the AGN. So what about star formation? So it has been found in these radio observations, and also in the color diagrams that the galactic center is also actually going through some star formation process. So the star formation rate was estimated to be 0.1 solar per year by Yusuf Jabir in 2009. But a more recent paper by Nogueras Lara, who have actually this is part of the galactic nucleus survey. They have about 80,000 stars, and they've plotted the color diagram and found that there exists a smaller branch of stars which cannot be explained if you don't have star formation happening more recently. So from this, they actually estimated that there must have been a more recent burst of star formation with a strength of 0.2 to 0.8 solar mass per year in last 30 million years or so. Okay, so we now know that there is both AGN. There has been AGN activity, and probably there was a small strength starburst period in the galactic center too. So what else can we get from this observations, that what else can we constrain about the Fermi bubbles? So this is where Miller and Bregman's oxygen 8 to 7 line ratio came into picture. So what they found is that this ratio was enhanced within the Fermi bubbles and started to go below and finally merged to the galactic, usually the static galactic halo level. So in this right plot, what you see is this different beams, which are basically this this elliptical beams that you see coming out from this galactic center. So in each bin, in the first bin, which encloses the Fermi bubble, the ratio is quite high, and towards the other, as soon as you go outside the Fermi bubble bin, the ratio goes down, and the ratio becomes consistent to the galactic CGM of 2 million Kelvin temperature. So from this, they actually estimated that the Fermi bubble temperature must be about 10 to the 6.6 Kelvin. So the mechanical luminosity must be about 2 to 10 to the 40, 2 times 10 to the 42 arcs per second. So we also did some simulation and found out synthetic line ratios, and the simulation says that you can also have the mechanical luminosity must be less than 10 to 41 arcs per second, and you can still produce this line ratio. So if you have more luminosity, then the line ratios really go more become even more than 1. So this is within an order of magnitude. These two estimates are really consistent, but it sets a limit where the luminosity can be because of the temperature of the oxygen 8 and 7 emitting gas. So again, so what is the origin of the Fermi bubble then? So the question of origin can be divided into two parts. One is the dynamical origin and one is the spectral origin. So the dynamical origin is more obvious, that what gave rise to the energy to these bubbles, whether it is a black hole or whether it is supernovae. In the spectral origin case, you can actually think that where does the gamma ray come from? Is it hadronic process? Is it electronic process? What is the main process that gives rise to the gamma rays? So you don't have to even go to too much details into the topic to find out something about the Fermi bubble. So what you see here is the spectrum of the Fermi bubble. Okay, spectrum of different components. So the blue one is actually the Fermi bubble spectrum. And you can immediately see that the after about 1 GeV, the spectrum flattens out and the spectrum goes as 10 to e to the minus 1.1, whereas before it is about e to the power 0.5. And just simply you perform a synchrotron, assume that it is emitted via inverse Compton process, and you can get from this dependence, you can easily get that the electron spectrum must be about minus 3.2, which is on this right side. And early before 1 GeV, the electron spectrum must be close to minus 2, which is again consistent with the electron spectrum estimated from the microwave haze radio emission. Okay, and this you can estimate what is the cooling time of such hard electron, and it turns out that this cooling time is a few million years. So these electrons have to be freshly accelerated, otherwise you would see that the electron spectrum would not be such hard. Okay, so there are actually different mechanisms that you can produce such Fermi bubbles. Like one way is that you can actually throw cosmic ray electrons from the galactic center and then let them reach to the height within 2 million years. So this will give you an idea of the velocity. Okay, this will also give you an idea what is the mechanical luminosity if such is the case. So in this case, the mechanical luminosity is about Eddington or slightly sub-Eddington. Another way you can produce the freshly accelerated electrons is that if you accelerate them right before the shock, this Fermi bubble. So in that case, L mechanical can be much smaller. Okay, so I'm just probably I'll not be able to talk about a lot about other other models, but we can talk about this in the discussion section. So I just wanted to highlight one of the models that I have been working on. So this is a simple star formation driven model, which what we do is we inject supernova at the galactic center and let it evolve into a halo. So in the left hand side you see density, on the right hand side you see temperature, and so you see that it actually drives a shock outwards, and it also has different shocks like reverse shock, one here, and also forms clouds at the contact discontinuity. So the picture that we were proposing was that cosmic rays are being injected here, and again being accelerated at the reverse shock here, and in the turbulence inside. Whereas the X-rays coming from the galactic, most of the X-rays coming from the shell, which is hot as well as very dense. I mean, dense compared to the bubble. So it actually leaves a shell-like feature. So this is just the X-ray projection of the simulation, and if you put the gamma ray emission in top of it, it just seems to be fitting with the observations, and the brightness also match quite nicely. So then let me know when to stop. Otherwise I can actually go on forever.
Well, let's talk about this model. It's really
okay. So this is another model by Young et al. I think the authors are also here in the audience. So they consider an AGN driven model, and it's a simple model. They have cosmic ray diffusion, etc. And you can see that this is also able to get what is the the shape of the Fermi bubble, and also the brightness of the Fermi bubbles. But in their case, they have a very luminous AGN, which is about Eddington, and the age of the Fermi bubble is about 0.3. So it is not very certain that what is right, what is the right age of the Fermi bubbles, or what is whether it is related to the X-ray shells or not. But I am hoping to discuss it more in the discussion session, or after the Erosita talk, and so in the later after party. But I think I hope that you got some take-home messages or some take-home notes about the Fermi bubbles, and will be able to start thinking about it soon. Yeah. So the current status of the Fermi bubble is this. So both the teams of supernova driven or AGN driven, they're constantly fighting that which is right, but no conclusion so far.
Okay. Great. That was a really nice overview. I will go back and watch that. That's very comprehensive, and I think we'll open it up for about 5 minutes here, and have any discussion. Also, I want to say that Kartick, just because it's recommended that maybe we combine the breakout sessions with eRosita. Would that be okay? Because it's so related that I think everyone would want to be here, and then have one breakout room for both of you.
I'm more than happy to do that.
Sounds good, because I think that nicely goes in. So let's talk about for 5 minutes about any discussions. Open it up.
Can I have a quick suggestion?
Sure.
Since we'll be posting all these slides, which are great, by the way, thank you, Kartick. I didn't at least catch all the references you were talking about, so I don't know whether they are on the slide or not. But before posting, it would be great if you also include them on the
there
slide.
Are references already in the slide.
There were. Okay, then I didn't see them. Fine.
I did not add a lot of the work research, which would be too much.
Okay.
But
okay,
I have
great. Thank you.
Yeah. I have a question. So you said there's a 300-year time scale in there based on X-ray echoes off the molecular cloud. Where does that come from? I was confused about that.
Where does that come from? Means the echo or the estimation?
So what happened 300 years ago?
I know. So, but the echo suggests that there's something happened in the toward the AGN. So you can actually and given the size, the solid angle of this echo, echoing clouds, and the distance from the galactic center, you can actually estimate what happened some few million years ago. Maybe this is the same event that actually gave rise to the this stellar cluster 6-7 million years ago, but just the luminosity is it has happened over time. So the luminosity is about 10 to 41 to 42 arcs per second.
Okay. Oh, okay. That's past. Okay, so it's from the event 6 mega years ago. But it's still.
It's just 300 million years was the just that, since it is the distance between the AGN Sagittarius A star and the molecular cloud, and that because we don't see any emission from the Sagittarius A star anymore. So this is the reason of this 300 years. Nothing more really.
Okay. Oh, great. if there's any, let's see. Oh, you know what? There might be some hands raised that I missed actually.
Yeah, there are.
Okay, yeah. Sorry. Whoever. Let's go with Rogman.
Hey, great job, Kartick. I had a question. Do you like, I know Jocelyn Hawthorne's paper argues for a jet, but do you know if there's additional evidence that there is a jet inside the Fermi bubble?
There is no, I mean, people have not actually concluded anything. So there was initial claim by Dobler, Finkbeiner that there is a jet, but later they also backed out from that claim. And Planck, later, 4 years data from the Ackermann et al., they also don't conclude that there is any jet. They actually say that there is, we find no evidence of the jet. So does that answer your question?
Yeah, thanks. I was just curious, what's the status?
And then Pratik, how about you ask your question?
Yeah, thanks. So I think this is about this 300 year ago enhanced X-ray activity from the Galactic Center. So these are fluorescence light, fluorescence emission, which is, the 300 years is just the difference, the light travel, the excess light travel time. And what this is just an example which shows that the Galactic Center black hole can be variable on a very short time scale, as short as 300 years. So it should not be a big surprise that there was something like millions of years ago, that you can have large variations in mechanical luminosity and, bolometric luminosity on even short time scales. So the present dimness should not be thought of as like a permanent state of the black hole.
I absolutely agree with that. How much would the black hole have to grow by? How much mass did it accrete relative to, it's 4 times 10 to the 6 solar mass to produce the Fermi and E Rosita bubbles?
Right. So again, depending on how much, what is whether it was Eddington rate or something, but you can get from the total energy, right? That the total energy is about 10 to 55 erg. So, if you, I don't know if you easily convert it to a total amount of mass in from it.
Let's do that. Let's do that calculation.
Yeah.
in the back, because
I cannot do it.
It's a small fraction, but it could have.
Yeah, it is a small fraction. Yes.
Still a significant amount. Which is really interesting. All right, I think what we will do is just I'll say
Wait, there's a quick question from Mary in the chat.
Okay.
It just are there metallicity estimates for the gas thought to be directly associated with the bubbles? Is what she asks in the chat.
So are you talking about the Fermi
bubbles? The bubbles themselves.
I guess I'm thinking mainly in the UV if there's any constraints, or I doubt it because you don't have H1, so you probably.
I think Rogman will be a better person to answer that question.
I can comment on it. So there are 2 published metallicity estimates. One is a halo star, which Hauck and Lehner's group published a while ago, and they had beautiful fuse data with Lyman limit systems. So that's a super solar metallicity. There is one we published at a slightly medium latitude, which was a 21 centimeter emission detection, and we found it to be a lower limit of 30% solar or higher. The problem with that estimate is that A, the lines were saturated, and B, we have big beam smearing effects. These are tiny clouds, and our GBT beam size is very big. There's an upcoming paper, which is not published yet, where we have much more metallicity estimate, and all of these seem to suggest there are lower metallicities. And that's a very surprising thing. And we're kind of speculating what's going on. One factor is beam smearing, which is a big problem. The second might be that some of the gas that is entrained might be entrained, they might be entrained a little bit higher up and not necessarily being driven up from the ISM itself. So those are still work in progress. We haven't published that one yet.
Yeah, I mean, I definitely think this can be a strong constraint over whether these clouds are actually associated, because you get even the intermediate velocity clouds 2 kiloparsecs up, they're solar metallicity, right? So if you're finding subsolar consistently, that fits in with the general high velocity cloud population, which is, to be honest, what I think some of these clouds might be rather than specific to that. But I'll be really interested to see how things evolve.
Yeah, I mean, they're all co-moving with the Fermi bubble. It's a question of where they got entrained. Is it a high velocity cloud which is sitting there and something hit them and they started accelerating, or they're coming from the galactic center itself?
Great. Well, let's turn it over. Kartick, thank you again. We'll have a breakout room after Marcus's presentation. So, yes, a round of applause. Oh, wow.